Picture this. A man spends his entire life perfecting the art of building bridges, revolutionizes an entire industry, and designs what would become the most famous bridge in the world. Then, just 3 weeks after starting his masterpiece, he's gone. This is the story of John Augustus Roebling, and how a seemingly minor accident set in motion one of the most dramatic engineering sagas in history. But here's what makes this tragedy even more haunting. Roebling didn't just die before seeing his bridge completed. He died knowing that his family would have to carry the impossible burden of finishing what he started. And he had no idea that his death would ultimately lead to the most unlikely engineering hero of the 19th century. Let me take you back to 1869, to the bustling docks of Brooklyn, where the East River separated two thriving cities. Manhattan and Brooklyn were distinct entities then, and crossing between them meant enduring crowded, dangerous ferry rides that could take hours in bad weather. But one man looked across that turbulent water and saw something different. He saw the future. John Augustus Roebling wasn't born to be America's bridge-building genius. He arrived from Germany in 1831 as Johann August Roebling, an idealistic young man who initially planned to become a farmer in western Pennsylvania. But Roebling possessed something rare, an engineer's mind trapped in a philosopher's soul. He had studied architecture and engineering in Berlin, but it was his experience with early suspension bridges in Bavaria that would change everything. What set Roebling apart wasn't just his engineering brilliance, but his revolutionary approach to materials. In the 1840s, most suspension bridges used iron chains or hemp rope, both notoriously unreliable. Ships' cables would snap, bridges would collapse, and public trust in suspension bridge technology was nearly destroyed. Roebling saw the problem clearly. The materials weren't strong enough, and more importantly, they weren't flexible enough to handle the dynamic forces that suspension bridges must endure. His solution was ingenious and would transform construction forever. Instead of using single thick cables, Roebling developed a process for spinning thousands of individual steel wires into massive cables. This wasn't just stronger than iron chain, it was fundamentally different. Each wire could move independently, distributing stress across the entire cable system. When one wire failed, thousands of others continued carrying the load. It was engineering redundancy at its most elegant. By 1869, Roebling had already proven his wire cable system worked. His railroad suspension bridge across Niagara Falls had been carrying fully loaded trains for 14 years without incident. His Ohio River Bridge at Cincinnati was pushing the boundaries of span length, but the Brooklyn Bridge would be different. This wouldn't just be another bridge, it would be the longest suspension bridge in the world, spanning 1,395 feet between towers and rising 130 feet above the water. The technical challenges were staggering. The East River wasn't just wide, it was treacherous. Tidal currents reached 8 knots, and the riverbed was a mixture of sand, clay, and solid rock that varied unpredictably. Ships traveled this route constantly, so the bridge had to be high, enough for the tallest masts to pass underneath. And unlike his previous bridges, this one would carry not just pedestrians and carriages, but eventually the heaviest railroad trains of the era. Roebling spent months at the proposed bridge site, taking measurements, studying tidal patterns, and calculating loads. He was meticulous to the point of obsession because he understood that this bridge would either cement his legacy or destroy it. The margin for error was essentially zero. On June 28, 1869, Roebling was standing on a Brooklyn dock positioning his surveying equipment to take final measurements for the tower locations. He was so focused on his calculations that he didn't notice the approaching Fulton ferry. The ferry's bumper caught his right foot, crushing it against the dock pilings. It should have been a minor injury. Roebling was tough, 63 years, old but still vigorous. His foot was mangled, but 19th century medicine could handle much worse. The problem was Roebling himself. He had developed an almost mystical faith in water therapy and homeopathic medicine. He refused conventional medical treatment, insisting that cold water applications and natural healing would be sufficient. For 3 weeks, as his foot festered and infections spread, Roebling remained convinced he could cure himself. His family pleaded with him to see a doctor, but he was stubborn. He had survived political revolution in Germany, built an industrial empire in America, and revolutionized bridge engineering. He wasn't going to be defeated by a crushed foot. But tetanus doesn't care about your accomplishments. As the infection ravaged his nervous system, Roebling's body began the horrific process of tetanic spasms. His muscles would contract violently, his jaw would lock, and breathing became agony. Still, even as he lay dying, he continued working on bridge calculations, dictating notes to his son Washington about cable specifications and foundation requirements. On July 22, 1869, John Augustus Roebling died, never knowing that his death would become the first chapter in an epic that would span 14 years, claim dozens of lives, and ultimately be completed by the most unlikely chief engineer in American history, his daughter-in-law, Emily. The cruel irony wasn't lost on those who knew him. Roebling had spent his life building bridges that would outlast him by centuries, but he wouldn't live to see his greatest achievement. His detailed plans, however, were so precise and comprehensive that they would guide every aspect of construction. In a sense, John Roebling would be building his bridge from beyond the grave. But this is just the beginning of our story. Because when Washington Roebling inherited his father's dream, he had no idea that the bridge would nearly kill him too, and that its completion would depend on a woman who wasn't supposed to be anywhere near a construction site. The Brooklyn Bridge wasn't just built with steel and stone. It was built with tragedy, determination, and the kind of human drama that makes the greatest engineering achievements possible. Next time, we'll explore how a Civil War veteran took on the most challenging engineering project in American history, and why the foundation work would prove even more dangerous than the battlefields Washington Roebling had survived. Imagine being 32 years old and suddenly inheriting the most ambitious engineering project in American history. Not just the plans, not just the responsibility, but the weight of your father's dying words echoing in your mind. This was Washington Roebling's reality in July 1869, and what happened next would test everything he thought he knew about engineering, leadership, and survival. But here's what makes Washington's story even more compelling. He was the only person alive who truly understood his father's revolutionary vision. And yet, taking on the Brooklyn Bridge would expose him to dangers that made Civil War battlefields seem safe by comparison. The question wasn't whether he could build his father's bridge. The question was whether it would kill him first. Washington. Augustus Roebling was never supposed to be a bridge builder. While his father John had spent decades perfecting suspension bridge technology, Washington had chosen a different path: war. As a Union Army engineer during the Civil War, he had built military bridges under enemy fire, designed fortifications, and operated reconnaissance balloons behind Confederate lines. He understood stress, pressure, and impossible deadlines, but battlefield engineering was fundamentally different from civilian construction. The skills that made Washington exceptional weren't just technical, they were human. He spoke German, French, and English fluently, which would prove crucial when managing immigrant workers from across Europe. He had learned to make life-and-death decisions quickly, a skill that would serve him well when construction crises demanded immediate solutions. Most importantly, he had inherited his father's perfectionist streak, but tempered it with practical military experience. When Washington examined his father's detailed plans for the Brooklyn Bridge, he realized the magnitude of what lay ahead. John Roebling had designed more than a bridge. He had conceived an entirely new approach to suspension bridge construction. The towers would rise 276 feet above the water, taller than any structure in the Western Hemisphere except for a few church spires. The main span of 1,195 feet would be 50% longer than any existing suspension bridge. But the real challenge lay hidden beneath the surface. The foundation work would require a technology that was revolutionary and terrifying: pneumatic caissons. These were essentially giant upside-down boxes, sealed chambers that would be sunk to the riverbed and filled with compressed air to keep water out while workers excavated inside. It was like creating an underwater construction site, but the physics were barely understood and the dangers were completely unknown. Washington spent months studying European caisson technology, particularly the work being done on bridge foundations, in France and Germany. What he learned was both encouraging and horrifying. Caissons could work, but they had already killed workers in Europe. Men were emerging from caisson work with mysterious illnesses, joint pain, paralysis, sometimes death. European engineers called it caisson disease, but nobody understood what caused it. The technical challenges were staggering. The Brooklyn side caisson would need to descend 78 feet below high water to reach solid bedrock. The Manhattan side would be even deeper. Each caisson would weigh thousands of tons and measure 168 by 102 feet, larger than most buildings of the era. Inside these chambers, men would work in compressed air that was 2 to 3 times normal atmospheric pressure, using hand tools to dig through sand, clay, boulders, and whatever else lay buried in the East River bottom. Washington's first major decision revealed his character. Rather than delegate the dangerous caisson work to subordinates, he insisted on going down himself. This wasn't bravado, it was leadership. He understood that asking men to work in conditions you wouldn't face yourself was a recipe for disaster. But it was also a decision that would nearly cost him everything. Construction began in January 1870, and immediately Washington faced challenges his father had never anticipated. The Brooklyn waterfront was a chaos of competing interests. Ferry operators who saw the bridge as a threat to their business, politicians who wanted their share of the construction contracts, and residents who feared the massive construction project would destroy their neighborhood. The caisson work began with optimism. The first workers descended into the compressed air chamber, and the initial excavation proceeded smoothly. The Brooklyn caisson settled gradually as tons of sand and debris were removed from beneath it. Washington established a complex system of signals between the surface and the underwater worksite, using bells and speaking tubes to coordinate the dangerous work. But as the caisson descended deeper, problems emerged. The compressed air necessary to keep water out created an alien environment. Sound traveled differently. Breathing became labored. Candles flickered strangely in the dense air. Workers reported feeling dizzy, disoriented. Some complained of joint pain after their shifts. Washington dismissed these as normal adjustment symptoms, but he was wrong. The first serious accident happened 6 weeks into construction. A worker named John Myers emerged from the caisson complaining of severe chest pain. Within hours, he was paralyzed from the waist down. 2 days later, he was dead. The cause was completely mysterious. Myers had been healthy, experienced, and careful. There was no visible injury, no obvious explanation for his sudden collapse and death. More cases followed. Men would finish their shifts apparently healthy, then collapse hours later with symptoms that ranged from joint pain to complete paralysis. Some recovered fully, others were permanently disabled, and some died. The immigrant workers, mostly Irish and German laborers supporting large families, couldn't afford to quit despite the dangers. They called the caisson the coffin and crossed themselves before descending each day. Washington found himself caught between impossible pressures. The board of directors demanded faster progress and lower costs. The workers demanded safer conditions and hazard pay. The press criticized every aspect of the project, from its cost to its engineering to its human toll. And through it all, Washington was spending more and more time in the caissons himself, trying to understand what was killing his men. The isolation was crushing. Unlike his father, who had been the unquestioned authority on suspension bridge construction, Washington was pioneering unknown territory. There were no textbooks on caisson disease, no experts to consult, no precedents to follow. He was making life and death decisions based on intuition and incomplete information, knowing that every choice could mean the difference between success and catastrophe. As 1870 wore on, Washington began experiencing symptoms himself. Joint pain, fatigue, moments of confusion. He attributed them to stress and overwork, but privately he wondered if he was developing the same mysterious illness that was claiming his workers. The irony wasn't lost on him. He had survived some of the bloodiest battles of the Civil War, only to be threatened by an invisible enemy in the depths of his own construction project. But Washington Roebling was his father's son. He had inherited not just John's engineering brilliance, but his stubborn determination The bridge would be built regardless of the cost. He had no idea that the real test of his leadership was still to come, and that completing his father's dream would ultimately depend on someone who wasn't even supposed to be at the construction site. Next time, we'll descend into the nightmare world of the pneumatic caissons, where men worked in conditions that resembled nothing less than a journey to the center of the earth, and where Washington Roebling would face the enemy that would change everything, the mysterious caisson disease that threatened to claim not just his workers, but his own life. Imagine descending into a chamber buried beneath the East River, where the air is so thick you can barely breathe, where candle flames dance in ways that defy physics, and where men emerge speaking of visions and nightmares. This wasn't science, fiction. This was the daily reality of building the Brooklyn Bridge foundations, and it was killing people in ways that 19th century medicine couldn't explain or prevent. But here's what makes this chapter of our story so haunting. The very technology that made the Brooklyn Bridge possible was slowly destroying the man who would make it famous. Washington Roebling was about to discover that some engineering challenges exact a price that no amount of planning can anticipate. The pneumatic caissons were marvels of engineering that resembled instruments of torture. Picture a massive wooden box, 168 feet long and 102 feet wide, built like a ship's hull but designed to sink. The top was sealed with thick timbers and iron plates, creating an airtight chamber. Compressed air was pumped in through tubes from the surface, creating enough pressure to keep the East River from flooding the workspace below. Workers entered through airlocks, essentially diving bells that allowed them to transition between normal atmospheric pressure and the compressed air environment inside the caisson. The process took several minutes each way, as their bodies slowly adjusted to the pressure changes. But nobody understood why this adjustment was necessary, or what happened when it went wrong. Inside the caisson, the environment was alien. Sound traveled differently in the dense air, making voices echo strangely. Breathing required conscious effort, as if the air itself had weight. Candle flames burned with unusual colors and patterns, creating an otherworldly atmosphere that some workers compared to being trapped inside a living creature. The work itself was backbreaking. Men used picks, shovels, and crowbars to break apart the riverbed material, which varied unpredictably from soft sand to clay packed hard as concrete, to massive boulders that had been deposited by glaciers thousands of years earlier. Everything they excavated had to be loaded into buckets and hauled to the surface through airlocks, a process that was slow, dangerous, and exhausting. Washington Roebling established work shifts of 4 hours maximum, believing that limiting exposure to the compressed air would protect his workers. He was wrong, but he had no way of knowing it. The science of decompression sickness wouldn't be understood for another 2 decades. All he knew was that men were getting sick, and the sickness seemed to get worse as the caissons descended deeper. The Brooklyn caisson presented the first major test. As it settled through the riverbed, workers encountered layers that told the geological history of New York Harbor. They dug through sand deposited by ancient rivers, clay laid down when the area was a shallow sea, and rocky debris left by retreating glaciers. But they also found unexpected obstacles: the remains of old ships, discarded machinery, and even human artifacts that spoke to centuries of human activity along the waterfront. At 40 feet below high water, the first cases of severe caisson disease appeared. Workers complained of joint pain so intense they couldn't walk. Some experienced paralysis that came and went unpredictably. Others suffered from what they called the staggers, a disorientation so severe they couldn't perform simple tasks. The Irish workers, drawing on folk knowledge of diving for shellfish, called it getting the bends, but nobody understood what caused it. Washington documented every case meticulously, searching for patterns that might explain the mysterious illness. He noticed that larger men seemed more susceptible than smaller ones. Workers who had been drinking alcohol before their shifts got sicker than those who hadn't. Men who rushed through the airlock process were more likely to develop symptoms than those who took their time. But the pattern that worried him most was the correlation between depth and severity. The deeper the caisson went, the worse the disease became. The Brooklyn caisson reached bedrock at 78 feet below high water. But the Manhattan side would prove even more challenging. The geological conditions were different, requiring the caisson to descend nearly 100 feet through layers of sand, silt, and decomposed organic matter that created a toxic environment. The compressed air necessary to keep water out at that depth approached 3 times normal atmospheric pressure. Fire was a constant terror in the caissons. The compressed air environment made everything more combustible, and any spark could create an inferno in the confined space. Washington implemented strict safety protocols. No smoking, no open flames except for carefully monitored candles and fire suppression equipment stationed throughout the workspace. But accidents were inevitable. The first major fire occurred in the Brooklyn caisson during the winter of 1870. A candle ignited some wooden debris, and within minutes the entire chamber was filled with smoke and flame. Workers fled toward the airlocks, but the fire spread faster than men could escape. 3 workers died from smoke inhalation, and several others were severely burned. The fire also damaged the caisson's wooden structure, requiring weeks of repairs and delaying the entire project. But it was the psychological toll that proved most devastating. Workers developed superstitions about the caissons, believing they were cursed or haunted. Some reported hearing voices in the compressed air, seeing figures that weren't there, or experiencing vivid hallucinations during their shifts. Modern science recognizes these as symptoms of nitrogen narcosis, but to 19th century workers, they seemed like evidence of supernatural forces. Washington began experiencing his own symptoms in early 1871. Joint pain that kept him awake at night, periods of confusion where he would forget where he was or what he was doing, severe headaches that made it difficult to concentrate on technical drawings. He attributed these to stress and overwork, but privately, he suspected he was developing the same disease that was claiming his workers. The Manhattan caisson proved even more treacherous. At 90 feet below high water, the compressed air pressure was so intense that workers could only remain in the chamber for 2 hours at a time. The decompression process took longer, and the symptoms of caisson disease became more severe and more frequent. Workers who had been healthy and strong began emerging from shifts as broken men, some permanently disabled, others facing slow, agonizing deaths. By the spring of 1871, Washington Roebling was spending most of his time in the caissons, personally, driven by a combination of engineering necessity and growing desperation. He needed to understand what was happening to his men, but every hour he spent in the compressed air environment brought him closer to becoming another casualty of his father's vision. The cruel irony wasn't lost on anyone who knew the family history. John Roebling had died from refusing medical treatment for a minor injury. Now his son was slowly poisoning himself with compressed air, driven by the same stubborn dedication that had defined the Roebling legacy. The bridge was being built not just with steel and stone, but with the systematic destruction of the men who were creating it. What nobody could have predicted was that Washington's growing incapacity would create an opportunity for the most unlikely engineering hero in American history. As the chief engineer became less able to manage the daily operations of the most complex construction project in the world, someone else would have to step forward. Someone who wasn't supposed to be there at all. Next time, we'll meet Emily Warren Roebling, a woman whose intelligence and determination would not only save the Brooklyn Bridge project, but challenge everything 19th century America believed about what women could accomplish in the world of engineering and construction. In the summer of 1872, the Brooklyn Bridge project faced a crisis that threatened to destroy everything. The chief engineer was bedridden, possibly dying from caisson disease. Construction had slowed to a crawl. Politicians were calling for investigations. And into this chaos stepped a woman who wasn't supposed to be there, who had no official title, and who would ultimately save the most important engineering project in American history. But here's what makes Emily Warren Roebling's story so extraordinary. She didn't just step in to help her husband. She became the bridge. For 11 years, she would be the crucial link between Washington's engineering genius and the brutal reality of construction, proving that the most important qualification for leadership isn't what's between your legs, but what's between your ears. Emily Warren had never planned to become an engineer. Born into a prominent military family, she was educated at Georgetown Visitation Convent, where she studied literature, languages, and the social graces expected of a 19th century lady. When she married Washington Roebling in 1865, she expected a life as an army officer's wife, not as the unofficial chief engineer of the world's most ambitious construction project. But Emily possessed something that formal engineering education couldn't teach: an intuitive understanding of how complex systems work. She had grown up around military logistics, watching her father and brothers coordinate massive operations where failure meant death. She understood that engineering wasn't just about mathematics and materials. It was about managing people, resources, and political pressures under impossible circumstances. When Washington's health began deteriorating in 1871, Emily initially served as his messenger, carrying instructions between their Brooklyn Heights home and the construction site. But she quickly realized that simply relaying information wasn't enough. The project needed someone who could understand the technical decisions, explain them to contractors and city officials, and make real-time adjustments when problems arose. So, Emily began educating herself. She studied her father-in-law's original plans, learning to read engineering drawings and understand structural calculations. She mastered the mathematics of suspension bridge design, from cable tension calculations to wind load analysis. Most importantly, she learned to speak the language of construction, the practical vocabulary of materials, methods, and measurements that separated theoretical engineering from actual building. The transformation wasn't immediate or easy. Emily spent her days at the construction site, dressed in the formal attire expected of a lady, but asking questions that revealed an increasingly sophisticated understanding of engineering principles. Workers who initially dismissed her as the chief's wife gradually began bringing her their technical problems directly, recognizing that she often provided better answers than the male supervisors. Emily's first major test came in 1873, when a corruption scandal threatened to destroy the entire project. City investigators discovered that J. Lloyd Hay, the contractor supplying wire for the bridge cables, had been substituting inferior materials to increase his profits. The revelation sent shockwaves through New York politics and raised serious questions about the structural integrity of the bridge itself. While Washington struggled with the physical effects of caisson disease, Emily took charge of the crisis. She coordinated with metallurgists to test the cable wire, worked with city engineers to assess the structural implications, and developed a plan to add additional safety cables that would compensate for the defective materials. Her technical analysis was so thorough and convincing that it satisfied both political critics and engineering experts. But Emily's greatest challenge wasn't technical, it was social. 1870s America had rigid ideas about what women could and couldn't do, and managing a major construction project definitely fell into the couldn't category. She faced constant skepticism from male contractors who refused to take orders from a woman, politicians who questioned her authority, and society columnists who criticized her for abandoning traditional feminine roles. Emily developed strategies that were brilliant in their subtlety. Rather than challenging male authority directly, she positioned herself as Washington's representative, speaking with his voice and authority. She learned to present her own engineering insights as if they originated with her husband, allowing prideful men to accept her decisions without losing face. It was a delicate balancing act that required not just technical competence, but exceptional emotional intelligence. The daily routine Emily established would have exhausted most people. She spent mornings at the construction site, reviewing progress and solving technical problems. Afternoons were devoted to meetings with city officials, contractors, and suppliers. Evenings found her at home with Washington, discussing engineering challenges and planning the next day's work. She was essentially functioning as chief engineer while maintaining the fiction that her bedridden husband was still in charge. Emily's technical contributions were substantial and innovative. When problems arose with the cable spinning process, she developed new quality control procedures that ensured consistent wire tension. She designed improved anchorage systems that better distributed the massive loads from the main cables. Most importantly, she managed the complex coordination between different phases of construction, ensuring that the stonework, cable installation, and deck construction proceeded in proper sequence. But perhaps Emily's most important contribution was simply showing up day after day for 11 years. Construction workers knew they could depend on her for answers, decisions, and support. City officials learned to respect her technical knowledge and political acumen. The bridge project survived its various crises largely because Emily provided the steady, competent leadership that kept thousands of people working toward a common goal. The personal cost was enormous. Emily essentially sacrificed her private life to the bridge, spending virtually every waking hour managing the project. She endured constant criticism from people who believed she was overstepping social boundaries. Most painfully, she watched. Her husband's health continued to deteriorate, knowing that the stress of the project was partly responsible for his condition. Yet Emily persevered, driven by a combination of family loyalty, personal pride, and genuine belief in the importance of the Brooklyn Bridge. She understood that this wasn't just about connecting two cities. It was about proving that American engineering could achieve the impossible. The bridge had become a symbol of national ambition and technological progress, and Emily was determined to see it completed regardless of the personal cost. By 1883, when the Brooklyn Bridge finally opened, Emily Warren Roebling had become the most accomplished female engineer in American history, though she would never receive official recognition for her achievements. She had managed a construction project that employed thousands of workers, cost $15 million, and required innovations in materials science, structural engineering, and construction management. The irony is profound. The Brooklyn Bridge, often celebrated as a monument to masculine engineering prowess, was actually completed by a woman whose intelligence, determination, and leadership proved that gender was irrelevant to engineering excellence. Emily had demonstrated that the most important tools in an engineer's toolkit aren't instruments or equations, but the ability to solve problems, manage complexity, and inspire confidence in others. If Emily's incredible story amazes you as much as it does me, smash that subscribe button and hit the bell icon. Her determination built more than just a bridge. It opened doors for women in engineering. Like this video if you're inspired, and drop a comment telling me which part of her story impressed you most. Don't forget to share this with someone who needs to hear about this engineering pioneer. Next time, we'll explore the revolutionary cable technology that made the Brooklyn Bridge possible and discover how a catastrophic fraud nearly brought down the entire project, just as Emily was proving that a woman could indeed build the world's greatest bridge. Picture this. You're standing 130 feet above the East River on a wooden platform barely 6 inches wide, with nothing but air between you and certain death. In your hands, you're guiding a single steel wire, one of 5,134 that will be bundled together to create a cable stronger than anything ever built. This was the daily reality for the cable workers of the Brooklyn Bridge, men who walked on air to weave the steel sinews that would hold up the world's greatest span. But here's what makes this chapter of our story so remarkable. The very technology that made these cables possible was invented by a man who died before he could see them installed. John Roebling's revolutionary wire rope system was about to be tested at a scale never before attempted, and any miscalculation would turn the bridge into a death trap for everyone who crossed it. The transition from foundation work to cable construction marked a fundamental shift in the Brooklyn Bridge project. Where the caisson work had been a battle against water and earth, cable spinning was a dance with wind and gravity. Emily Roebling now faced challenges that were completely different, but equally dangerous. Coordinating the most complex cable installation in engineering history, while ensuring that every wire met standards that had never been tested at this scale. John Roebling's wire rope innovation wasn't just about strength. It was about redundancy. Traditional suspension bridges used iron chains or thick rope cables, creating single points of failure that could collapse an entire span. Roebling's system distributed the load across thousands of individual steel wires, each capable of carrying its share independently. If one wire snapped, the others would compensate. It was engineering elegance at its most practical, but manufacturing these wires to Roebling's specifications required precision that pushed 1870s metallurgy to its limits. Each wire had to be exactly 0.196 inches in diameter, with a tensile strength of at least 160,000 pounds per square inch. The steel had to be free of impurities that could create weak points, and the wire drawing process had to create a perfectly smooth surface that would allow thousands of wires to slide against each other without friction wear. The J.A. Roebling's Sons Company in Trenton, New Jersey, had been perfecting this wire manufacturing process for decades, but the Brooklyn Bridge represented an order of magnitude unlike anything they had produced before. The 4 main cables would require over 3,500 miles of individual wire, enough to stretch from New York to London. Every mile had to meet identical specifications because a single substandard wire could compromise the entire structure. Emily personally oversaw the quality control process, establishing testing, procedures that went far beyond industry standards. Sample wires were subjected to tension tests that exceeded the maximum loads they would face in service. She instituted random inspections of wire coils, rejecting entire shipments if defects were discovered. Her attention to detail bordered on obsession, but she understood that the margin for error was essentially zero. The cable spinning process itself was a marvel of coordination and courage. Workers began by stringing temporary footbridges between the completed towers, creating narrow walkways that swayed sickeningly in every breeze. These bridges were only 6 inches wide and had minimal railings, making every step a potentially fatal decision. Workers called them death traps, but they were essential for guiding the spinning wheels that would lay each wire in its precise position. The spinning process started with a single wire stretched between anchorages, passing over the towers and forming the basic geometry of the suspension system. Additional wires were added one at a time, with workers using specialized wheels to ensure proper spacing and tension. Each wire had to follow exactly the same path, creating the perfectly uniform curve that would distribute loads evenly across the entire cable. Weather was a constant enemy. High winds made the footbridges so unstable that work had to be suspended for safety. Rain created slippery conditions that were deadly at such heights. Winter ice formed on the wires, making them difficult to handle and dangerous to touch with bare hands. Emily established detailed weather protocols, but the pressure to maintain construction schedules often forced workers to take risks that would be unthinkable by modern safety standards. The first major crisis came in the spring of 1878, when inspectors discovered evidence of wire fraud. J. Lloyd Hay, the contractor supplying wire for the cables, had been substituting inferior materials to increase his profits. Some of the wire installed in the cables had tensile strength significantly below specifications, potentially compromising the entire structure. Emily faced an impossible choice. Removing the defective wire would require partially dismantling cables that had taken months to install, setting the project back years and costing hundreds of thousands of dollars. But leaving substandard wire in place could result in catastrophic failure when the bridge opened to traffic. The decision she made would determine whether the Brooklyn Bridge became a triumph or a tragedy. Working with consulting engineers, Emily developed an innovative solution. Rather than removing the defective wire, she ordered the installation of additional cables that would provide a substantial safety margin. The bridge would be stronger than originally designed, compensating for any weaknesses in the fraudulent materials. It was a decision that required both engineering insight and tremendous courage, because she was betting the project's success on her own technical judgment. The cable fraud scandal also revealed Emily's political acumen. She managed the crisis, communication carefully, providing enough technical detail to satisfy engineering critics while avoiding the kind of sensational coverage that could destroy public confidence in the project. Her handling of the scandal actually enhanced her reputation, demonstrating that she could manage both technical challenges and political pressures with equal skill. By 1880, the 4 main cables were complete, each containing 5,434 parallel steel wires bundled into a structure 15.75 inches in diameter. The combined strength of these cables was extraordinary. They could theoretically support a load of 24,000 tons, far exceeding the maximum weight the bridge would ever carry. Emily had overseen the installation of what were essentially the strongest cables ever created, using technology that represented the pinnacle of 19th century materials science. But the completion of cable work marked only the midpoint of the bridge construction. The most visible and politically sensitive phase was still ahead, building the roadway deck that would actually carry traffic, and that work would bring new challenges that would test everything Emily had learned about engineering, management, and survival in the unforgiving world of major construction. Next time, We'll explore how the bridge's iconic Gothic towers rose from the river, creating architectural landmarks that were as much about beauty as engineering, and discover why building these massive stone structures required innovations that pushed masonry construction to its absolute limits. Imagine trying to build a cathedral while standing in a river. That's essentially what Emily Roebling faced when construction shifted to the bridge's towers. Massive Gothic structures that had to be both architectural masterpieces and engineering marvels, rising 276 feet above the water while supporting loads that no masonry structure had ever been asked to bear. But here's what makes this phase of construction so extraordinary. These weren't just towers, they were statements. In an era when America was still proving itself to the world, these Gothic giants would announce that American engineering could create structures as beautiful as they were functional. The question was whether Emily could build them without losing everything her family had already sacrificed. The tower construction began in 1872, just as Emily was establishing herself as the project's de facto chief engineer. Unlike the hidden Kassenwerk, tower construction would be visible to everyone in New York. Every mistake, every delay, every accident would be scrutinized by critics who were already questioning whether a woman could manage such a massive undertaking. Each tower was designed to be a monument to both engineering precision and architectural beauty. John Roebling had specified Gothic revival styling not just for aesthetics, but because the pointed arches and flying buttresses were structurally efficient ways to distribute the enormous loads from the suspension cables. The towers would each weigh 90,000 tons and stand taller than any structure in the Western Hemisphere except for a few church spires. The limestone blocks came from quarries in Maine, each one carefully selected for strength and appearance. Transportation was a logistical nightmare that required coordinating ships, barges, and specialized lifting equipment. Emily personally inspected major shipments, rejecting stones that showed any signs of weakness or inconsistency. She understood that the towers would be judged as much for their beauty as their engineering, and any visible flaws would undermine public confidence in the entire project. The masonry work required craftsmen whose skills bridged medieval stone-cutting traditions and industrial precision. Each block had to be cut to exact specifications, with tolerances measured in fractions of inches. The Gothic details, from pointed arches to decorative tracery, were carved by hand, using techniques that hadn't changed substantially since the great cathedrals of Europe were built centuries earlier. But these weren't medieval cathedrals. The Brooklyn Bridge towers had to support dynamic loads from moving traffic, resist wind forces that could exceed hurricane strength, and accommodate the massive mechanical stresses from the suspension cables. Emily worked with structural engineers to ensure that every decorative element also served an engineering function, creating towers that were simultaneously beautiful and brutally functional. Winter construction presented challenges that tested everyone's endurance. New York winters in the 1870s were harsh, with temperatures dropping well below zero and ice storms that made construction work nearly impossible. Mortar wouldn't set properly in freezing weather, stone became brittle and difficult to work, and workers faced constant danger from ice-covered scaffolding and equipment. Emily established heated workshops where masons could prepare stones during the worst weather, but the actual construction had to continue regardless of conditions. Workers developed techniques for protecting fresh mortar with heated covers, and Emily instituted hazard pay for men willing to work in dangerous winter conditions. The human cost was substantial, but stopping construction would have meant losing an entire building season. The most critical engineering challenge was ensuring perfect alignment between the two towers. They were being built simultaneously on opposite sides of the river, but they had to be positioned with absolute precision to support the suspension cables properly. Any deviation would create uneven loads that could cause catastrophic failure when the bridge was completed. Emily established a sophisticated surveying system using telescopes and precisely calibrated instruments to monitor tower construction progress. Weekly measurements verified that both towers were rising at the same rate and maintaining perfect alignment. The margin for error was essentially zero. Even a few inches of deviation could make the suspension system impossible to install correctly. The Gothic detailing required extraordinary coordination between artistic vision and engineering reality. Each pointed arch had to be not just beautiful, but precisely positioned to channel loads from the suspension cables into the tower foundations. The decorative stonework wasn't mere ornamentation. It was an integral part of the structural system, designed to distribute stresses in ways that would prevent cracking or failure under the enormous loads the towers would bear. Public fascination with the towers grew as they rose above the New York skyline. Newspapers published daily progress reports, and crowds gathered to watch the construction work. Emily found herself in the unusual position of managing not just a construction project, but a public spectacle that symbolized American technological achievement. The personal pressure was enormous. Every decision Emily made was scrutinized by engineering experts, political critics, and newspaper reporters looking for evidence that a woman couldn't handle such responsibility. She responded by becoming even more meticulous in her planning and execution, establishing standards that exceeded anything required for similar projects. By 1876, both towers were complete, rising like Gothic cathedrals from the East River, and creating one of the most recognizable skylines in the world. They were architectural triumphs that demonstrated American craftsmanship could rival anything produced in Europe. But more importantly, they were engineering achievements that proved the fundamental design of the Brooklyn Bridge was sound. Tower completion marked a psychological turning point for the entire project. The most visible and dramatic phase of construction was finished, and Emily had proven that she could manage large-scale masonry work as effectively as she had handled the technical challenges of foundation and cable construction. The bridge was beginning to look like the revolutionary structure John Roebling had envisioned. But the towers also represented a new kind of pressure. With these Gothic giants dominating the New York skyline, there was no turning back. The bridge had to be completed, and it had to work perfectly, because failure would now be visible to millions of people. Emily had built monuments that announced to the world that the Brooklyn Bridge would be America's greatest engineering achievement. Now she had to make sure it actually functioned. Next time, we'll uncover the scandal that nearly destroyed everything. The discovery that hundreds of tons of defective cable wire had been secretly installed in the bridge, creating a crisis that threatened not just the project, but Emily's reputation and the safety of everyone who would eventually cross her bridge. Picture Emily Roebling's horror when she discovered that 600 tons of defective wire had been secretly woven into the cables of her bridge. Wire that could snap under load. Wire that could turn the Brooklyn Bridge into a death trap for thousands of people. This wasn't just engineering failure. It was betrayal at the most fundamental level, and it threatened to destroy everything the Roebling family had sacrificed to build. But here's what makes this crisis so remarkable. The very scandal that nearly ended the Brooklyn Bridge project would ultimately lead to innovations that made it stronger than anyone had ever imagined. Sometimes the greatest engineering achievements come not from perfect execution, but from overcoming catastrophic problems with solutions that nobody thought possible. The discovery began with routine quality inspections in the spring of 1878. Emily had established rigorous testing protocols that went far beyond industry standards, randomly selecting wire samples for tensile strength analysis. When several samples failed dramatically below specifications, she initially assumed they were statistical anomalies, but as more tests revealed similar problems, a horrifying pattern emerged. J. Lloyd Hay, the contractor supplying wire for the bridge cables, had been systematically substituting inferior materials to increase his profits. Instead of the high-grade steel specified in the contracts, Hay had been delivering wire made from cheaper materials that looked identical but had significantly lower tensile strength. The fraud had been ongoing for months, and an estimated 600 tons of substandard wire was already installed in the bridge cables. Emily's first reaction was disbelief, then fury, then cold calculation. She understood immediately that this wasn't just a business scandal. It was a potential catastrophe that could kill thousands of people if the bridge failed under load. The cables were the heart of the entire suspension system, and any weakness could trigger a progressive collapse that would send the entire structure into the East River. The political implications were equally devastating. Critics who had always opposed the bridge project seized on the scandal as evidence that the entire undertaking was corrupt and dangerous. Newspaper headlines screamed about death traps and criminal negligence. City officials called for investigations that could result in construction being halted permanently. Emily found herself defending not just the technical integrity of the bridge, but the entire Roebling legacy. Working with consulting engineers, Emily began a comprehensive analysis of the cable system's structural capacity. The mathematics were complex and terrifying. Each main cable contained 5,434 individual wires, and determining the exact location and quantity of defective wire required detailed records that didn't always exist. The analysis had to account for dynamic loads from wind and traffic, stress, concentrations at attachment points, and safety factors that would protect against catastrophic failure. The engineering calculations revealed a mixed picture. The defective wire significantly reduced the cable's theoretical strength, but the bridge design included substantial safety margins that might compensate for the weakened materials. The question was whether might was acceptable when dealing with a structure that would carry thousands of people daily. Emily faced an impossible choice: halt construction and remove the defective wire, or find another solution that would ensure public safety. Removing the contaminated wire would have been catastrophic for the project. The cables had taken years. To install and partially dismantling them would mean starting the cable spinning process almost from scratch. The delay would cost millions of dollars and could easily stretch construction by another 5 years. More importantly, the political fallout might generate enough opposition to cancel the entire project permanently. Emily's solution was characteristically bold and innovative. Rather than removing the defective wire, she proposed installing additional safety cables that would provide redundancy far beyond the original design specifications. The bridge would have not just 4 main cables, but also diagonal stay cables that would distribute loads differently and provide backup support if any component failed. The technical analysis supporting this decision required calculations that pushed 19th century structural engineering to its limits. Emily worked with mathematicians and materials scientists to model stress distributions, failure modes, and safety factors that had never been considered for suspension bridge design. The additional cables would actually make the bridge stronger than John Roebling's original specifications, creating a hybrid suspension system that combined the best features of multiple design approaches. Implementing this solution required political courage as much as engineering insight. Emily had to convince city officials, insurance underwriters, and the general public that adding cables was better than removing defective wire. She prepared detailed technical presentations that explained the mathematics of structural redundancy, demonstrating that the modified design would be safer than the original, even with the contaminated materials in place. The cable fraud scandal also revealed Emily's exceptional crisis management skills. She controlled information flow carefully, providing enough technical detail to satisfy engineering critics while avoiding sensational coverage that could destroy public confidence. She established new quality control procedures that would prevent similar problems, and she personally oversaw the installation of the additional safety cables. The modified cable system that emerged from the scandal was actually superior to the original design in several important ways. The additional cables provided multiple load paths that would prevent progressive collapse even if major components failed. The hybrid suspension design became a model for future bridge construction, influencing engineering practice for decades to come. What had started as potential disaster became genuine innovation, but the personal cost to Emily was enormous. The scandal occurred just as she was gaining recognition as a competent engineer in her own right, and the crisis forced her to prove herself all over again under intense public scrutiny. She spent months working 18-hour days, coordinating technical analysis, managing political pressure, and overseeing the installation of additional cables that would restore confidence in the project. The resolution of the cable scandal marked a turning point in public perception of both Emily and the Brooklyn Bridge. Her handling of the crisis demonstrated technical competence, political skill, and personal integrity that silenced most critics. The bridge emerged from the scandal stronger both structurally and politically, with public support that would sustain the project through its final phases. By late 1878, the cable modifications were complete, and the Brooklyn Bridge possessed what was arguably the most robust suspension system ever constructed. Emily had transformed a potentially fatal flaw into a competitive advantage, proving that great engineering sometimes requires not just building things right the first time, but fixing them brilliantly when they go wrong. Next time, we'll witness the culmination of 14 years of struggle, sacrifice, and innovation as the Brooklyn Bridge finally opens to the public, creating one of the most memorable celebrations in New York history and establishing a monument that would inspire engineers and dreamers for generations to come. May 24th, 1883. After 14 years of death, scandal, and seemingly impossible challenges, the Brooklyn Bridge was finally ready to open. But as Emily Warren Roebling prepared for what should have been her greatest triumph, she had no idea that opening day would bring both celebration and tragedy, and that the bridge's first week would nearly end in disaster that could have destroyed everything she had worked to build. This is the story of how the world's greatest bridge almost failed, not because of engineering problems, but because of human psychology, and how one woman's quiet courage ultimately secured a legacy that would inspire generations of engineers and dreamers around the world. The morning of May 24th, 1883, dawned clear and warm. Perfect weather for what New York newspapers were calling the greatest celebration in the city's history. President Chester Arthur had traveled from Washington specifically for the opening ceremony. Dignitaries from across America and Europe gathered to witness what many considered the eighth wonder of the world. But for Emily, the day carried emotions too complex for any public celebration to capture. Emily had insisted on a symbolic honor that spoke to everything she had sacrificed for this moment. She would be the first person to cross the completed Brooklyn Bridge, not in some ceremonial capacity, but as the engineer who had made it possible. Carrying a rooster for good luck, a tradition from her childhood, she walked across the span that had consumed 14 years of her life, feeling the solid deck beneath her feet and the gentle sway of the suspension system responding to wind and load exactly as the calculations had predicted. The technical achievement was staggering by any measure. The Brooklyn Bridge was not just the longest suspension bridge in the world, spanning 1,595 feet between towers, but also the first to use steel cables instead of iron. The four main cables contained over 14,000 miles of individual wire, enough to stretch halfway around the earth. The Gothic towers rose 276 feet above the water, taller than any structure in the Western Hemisphere except for church spires. The total cost had reached $15 million, equivalent to over $400 million today, but the numbers only told part of the story. Emily understood that the Brooklyn Bridge represented something far more significant than engineering specifications. It was proof that American technology could achieve the impossible, that suspension bridge design had reached a new level of sophistication, and that projects requiring unprecedented coordination and innovation could succeed despite political opposition, technical setbacks, and personal tragedy. The opening ceremony was designed to showcase both the bridge's engineering excellence and its symbolic importance to American technological progress. President Arthur's speech emphasized the bridge as a monument to American ingenuity and determination. Military bands played patriotic music while crowds cheered from both shores of the East River. Fireworks lit the sky as the sun set, creating a celebration that contemporary newspapers described as surpassing anything in New York's history. But the euphoria was short-lived. Just 6 days after the triumphant opening, the Brooklyn Bridge faced its first real test of public confidence, and the results were nearly catastrophic. On May 30th, 1883, Memorial Day, massive crowds gathered on the bridge to watch naval exercises in the harbor below. The pedestrian walkway, designed to accommodate normal foot traffic, became dangerously overcrowded with thousands of people. Someone in the crowd shouted that the bridge was collapsing. The claim was completely false. The structure was performing exactly as designed, with normal flexing under load that indicated healthy structural response. But panic spread through the crowd with terrifying speed. People began pushing toward the exits, creating a human stampede that turned the bridge deck into a death trap more dangerous than any engineering failure. 12 people were killed and dozens more injured in the stampede, trampled by crowds fleeing from an imaginary threat. The irony was devastating. The bridge that had been designed to save lives and connect communities had become the site of tragedy caused not by engineering failure, but by public misunderstanding of how suspension bridges were supposed to function. Emily watched the aftermath with a mixture of grief and frustration. The stampede deaths were preventable tragedies that had nothing to do with the bridge's engineering, but everything to do with public education about suspension bridge behavior. She realized that building the bridge had been only half the challenge. The other half was teaching people to trust and understand the technology that would serve them. The solution to the confidence crisis came from an unexpected source: P.T. Barnum, the famous circus promoter. Barnum offered to march a herd of 21 elephants across the Brooklyn Bridge to demonstrate its stability and safety. The spectacle was pure showmanship, but it was also brilliant psychology. If the bridge could support 21 elephants walking in formation, it could certainly handle normal human traffic. The elephant parade took place on May 17, 1884, almost exactly 1 year after the bridge opening. Crowds gathered to watch as Barnum's circus animals, led by the famous elephant Jumbo, walked majestically across the span. The bridge performed flawlessly, with no unusual movement or stress. More importantly, the visual demonstration restored public confidence in a way that no amount of technical explanation could have achieved. Emily watched the elephant parade with mixed emotions. She was relieved that public confidence had been restored, but frustrated that engineering excellence required circus theatrics for validation. The incident highlighted a challenge that engineers still face today: the gap between technical reality and public perception, and the difficulty of communicating complex engineering concepts to people without technical background. The long-term impact of the Brooklyn Bridge extended far beyond its immediate function as a transportation link. The engineering innovations developed for the project, from pneumatic caisson construction to steel cable spinning, became standard practice for bridge construction worldwide. The project management techniques that Emily had developed for coordinating complex construction work influenced infrastructure projects for decades to come. Perhaps most importantly, the Brooklyn Bridge proved that American engineering could achieve anything if supported by adequate planning, funding, and determination. The project inspired a generation of engineers to attempt increasingly ambitious undertakings, from skyscrapers to transcontinental railroads to ultimately the Panama Canal and beyond. For Emily personally, the bridge opening marked both an ending and a beginning. She had spent 14 years of her life managing the most complex engineering project in American history, proving that gender was irrelevant to engineering competence and leadership ability. But she had also sacrificed her personal life and privacy to an extent that few people could understand or appreciate. Emily never received official recognition as the Brooklyn Bridge's chief engineer, though everyone involved in the project understood her crucial role. She had operated in a world that didn't acknowledge women's technical capabilities, finding ways to exercise real authority while maintaining the social fictions that allowed men to accept her leadership. Her success opened doors for future generations of women in engineering, though progress would be slow and often frustrating. The Brooklyn Bridge stands today as one of the most recognizable landmarks in the world, carrying millions of people annually and serving as a symbol of human achievement and technological progress. Every person who crosses it walks in the footsteps of Emily Warren Roebling, the woman who saved America's greatest bridge through intelligence, determination, and courage that transcended every barrier placed in her path. The story of the Brooklyn Bridge is ultimately a story about human potential. What becomes possible when technical excellence, personal determination, and moral courage combine to overcome seemingly impossible challenges. Emily Roebling proved that the most important qualifications for engineering leadership have nothing to do with gender, and everything to do with the ability to solve problems, inspire confidence, and never give up when the stakes are highest. And there you have it, the incredible 14-year saga of the Brooklyn Bridge. This wasn't just about building a bridge, it was about human determination, engineering innovation, and breaking barriers. If this series showed you something new about one of the world's most iconic structures, please subscribe to see more engineering marvels broken down like this. Hit that like button if you enjoyed the journey from tragedy to triumph, share this series with fellow engineering enthusiasts, and let me know in the comments which episode was your favorite and what engineering marvel you'd like to see next. Thanks for joining me on this incredible journey through history.